Hey, honors geometry. These are going to be the 1.2 notes. All right, we're talking about line segments and distance today. So a line segment is just part of a line. So if we think about a line, all right, make sure you're using your rulers for this. But instead of the whole line, we're actually just looking at a portion of it. All right, so we take 2 points. We can call them A and B, or you can label them whatever you want. But then we really don't want the arrows on either end, right? This is called line AB. And within line AB does exist segment AB, all right? But for our purposes here, we really just care about the distance, or sorry, the segment that's in between them, all right? So this would be segment AB, and we would call this AB with the segment hat on top. So when it's a line, the line has arrows on either end for the hat. When it's a segment, it does not have arrows on either end. All right, that's line segment AB. You could also call it BA. That would also work. The segment addition idea comes along with the idea of betweenness of points. So if I draw 2 points here, again, let's call them A and B. The idea of something being between, we want it to be very clear. You know what I mean? So if I were to draw a point over here, it kind of looks like it's in between A and B. Or if I were to draw a point further down here, it's sort of in between A and B, but maybe not as much in between. And then you can think if I drew a point way at the bottom of the page, you know, is that really between the points? And so we really want to be specific about what it means to be in between. So for a point to be in between two other points, it has to be, first of all, collinear. All right. So if point C is between points A and B, then we know that A, B, C are collinear. And we have to know one other thing. We know, and this is where the segment addition comes into play, we know that if I take AC plus CB, that would give me this entire distance AB. All right, so the rule is that AC plus BC is going to equal AB. All right, so in order for a point to be between two other points, those 3 points have to be collinear, and then they obviously the piece on the left plus the piece on the right would equal the whole piece. All right, the idea of things being congruent, okay? Things are congruent if they have exactly the same shape and exactly the same size, okay? So what that means is I could take 2 triangles, okay, like one like this, and if I take this triangle, whoops, let me paste that there. All right, so if let's hold on one sec. All right, let me try that again. So if I draw a triangle, there we go, and I'm gonna copy this. Okay, and if I rotate it like this, so I'm taking the exact same shape, and if I rotate it, or if I were to do like a reflection across an axis, or if I were to, you know, reflect, translate, rotate, any of those transformations, we would have 2 congruent figures, okay? And so what we would do if I call this A, B, C, we would want to try to match up the corresponding sides. So this would be A, B, or sorry, let's call it D, E, F. All right, and so we could say something like triangle ABC is congruent. All right, so this is the symbol for congruent here, triangle DEF. All right, so these 2 figures are congruent because they have exactly the same shape and the same size. All right, the idea of equal versus congruent is a big one. All right, this will come up a lot when we do proofs. So I like to think of equal. Obviously, we know equal is the equal symbol, and then congruent again is this symbol here. But we use equal when we talk about numbers. All right, so lengths are equal, like when we talk about algebra, right? Like 8 plus 2 equals 10. It wouldn't make sense to say that 8 plus 2 is congruent to 10, right? So I'll do 8 plus 2 equals 10, right? We use the equal symbol. It would not make sense to say that 8 plus 2 is congruent to 10. All right, that's a no. That's a yes. All right. So whenever we work with numbers in algebra, we like to say that things are equal, okay? However, when I'm talking about things being congruent, I'm again talking more of like a quality, right? So things being equal in algebra is more of a quantity, and things being congruent is more of a quality. We're talking about how they are, how they're oriented, and what shape they are, and what size they are, all right? So if things are congruent, again, you wouldn't say that numbers are congruent. You would just say that numbers are equal. Same thing, you wouldn't say that triangles are equal to each other. Like if we took this statement up here and said that triangle ABC is equal to triangle DEF, that really wouldn't make any sense, okay? So that's the difference between equal and congruent. We're going to see quite a bit of that. Now, distance on a number line, this is going to be pretty quick. So obviously if we drew a number line, and we have 2 points on that number line, like let's say, -10 and +13. Obviously, I could just count until I get to 13, and I'd find out, oh, the distance is, 26 units. Sorry, 23 units. All right, so 23 units there. Now, obviously, I don't expect you to draw a number line every single time you do this, okay? The idea is that the distance between any 2 points, all right, the distance between any 2 points is the absolute value of the difference. Okay, so if I have 2 points, let's say -10 and 13, I'm going to take the absolute value of the difference, right? So one of my numbers goes in front. Let's put the -10 out in front, and the other number goes behind 13. All right, so if I have the absolute value of -10 minus 13, this would be like the absolute value of -23, which is just 23. It actually doesn't matter which order you put the numbers, right? So I could take the absolute value of the difference of 13 minus -10. Well, same situation. Now I've got the absolute value of +23, which is just 23. Okay, so when you're finding the distance between 2 points on a number line, what you always want to do is you want to subtract the values, right? Subtract them in either order, doesn't matter. Subtract the values and then take the absolute value. All right, now distance on the coordinate plane, all right? I honestly do not like the distance formula, all right? A lot of you memorized it. If you haven't memorized, excellent. I'm never going to tell you the distance formula. If you want to memorize it, you can, but that's up to you, all right? The distance formula I don't like because it's just a formula and you lose sight of why you plug in numbers where and what everything means. But if you realize that the distance formula is really just the Pythagorean theorem, all right? This right here is called the Pythagorean theorem. Okay, this will come up quite a bit throughout the geometry year. But a squared plus b squared equals c squared is called the Pythagorean theorem. And we use the Pythagorean theorem whenever we have a right triangle, all right? And so in my right triangle, if I draw a quick sketch of a graph here, all right, I could draw something like this. We've got a right triangle here. There's my right angle. So the short side, it doesn't matter which short side you start with, but let's call this side A, we'll call this short side B, and we'll call this long side C, all right? C is always the longest side. It's called the hypotenuse. And so I could graph a triangle anywhere I want. And really what I'm doing is I'm looking and trying to find out C, okay? Because C is really going to be the distance between those 2 points. So I'm going to redraw this actually. I'm going to make a new graph, a new drawing. And I'm going to keep the same type of triangle I've got. I'm going to keep that right triangle there. But instead of using A, B, and C, I'm going to use some letters that make a little bit more sense in the coordinate plane. So I'm going to call this horizontal distance X. I'm going to call the vertical distance Y. And I'm going to call the distance between the 2 points D for distance. Okay, so now we've got this formula, which is going to say that x squared plus y squared equals the distance squared. Okay, but I can even get more specific than that, right? Because if I'm looking for x or if I'm looking for y, I can actually use a little bit of some quick arithmetic here, right? So if I draw this one last time, all right, we're going to get our right triangle in here. Okay. Instead of saying that this horizontal distance is x, I know, let's say for example, this point here was located at 6 comma something, and this point here was located at, let's say, 2 comma something. So I know that the horizontal distance between 2 and 6 is 4, right? And how did I get the 4? Well, what I did when we look at distance, right, we know that we have to take the difference of the absolute value. So 6 minus 2 is 4. Absolute value of 4 is still 4, right? So I know this distance is 4 here because I subtracted those values. Now this is a pretty specific case, right? We want to know what happens in a generic case with just x's and y's. So that means what I can do is I can call this point x2 and this point over here x1. And for my y values, I can do kind of the same thing, right? I can call this point up here y2, and this point down here can be y1. And so if I look at the horizontal distance, we know the horizontal distance is x2 minus x1. And this vertical distance is going to be y2 minus y1. All right. So now if I look back at my formula and transform it one more time, we should be able to see that the distance squared, let me write it the other way here. We should know that x2 minus x1 squared plus y2 minus y1 squared equals the distance squared, right? That is a squared plus b squared equals c squared. That's the Pythagorean theorem. And all we have to do now is organize this one last time, right? If I take the square root of both sides, that will just give me the distance, right? I can use a square root to undo a square. So if I rewrite this now, we end up with the distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, and there is your distance formula. All right, so feel free to use the distance formula if you want, but I think it's a little bit easier to use the Pythagorean theorem. Okay, so you can go with either option if you want, but I think it's easier to use the Pythagorean theorem. Okay, for example, all right, let's say I wanted to find the distance between, let's go with, let's say, -3 comma 7, and let's make another point. Let's make this other point 2 comma, how about -5? All right, so I want to find the distance between these. So all I have to do is look at the difference between the x's, and I have to look at the difference between the y's. All right, that's all I have to do, and then use Pythagorean theorem, right? So if I use a squared plus b squared equals c squared, well, remember, a is just the difference between the x's. So what do I have to do to get from -3 to +2? Well, I'm increasing by 5. So a would be 5. And then what do I have to do to get from 7 to -5? Well, I'm going down by 12. And again, the distance is always going to be considered positive because it's the absolute value. So I don't even need to worry about it being a -12. I can just put in a +12. And now I can solve this for c. All right. So we've got 25 plus 144 equals c squared. I can continue with this and say that 169 equals c squared. To get rid of the c squared, I have to take a square root of both sides. And that's going to tell me that 13 units is going to be the distance between those 2 points. And there you go. All right. Sometimes when you do this, you might get a radical. Just make sure that you reduce the radical. All right. So if you have any perfect squares inside the radical, make sure you take out your perfect squares, and then you should be good. All right. Thank you for watching the 1.2 notes, and I will see you guys in class.